Hey guys, I want to take a look at this simulation with you. When I first look at the simulation, I can see I've got a glass of solid water. Sometimes that's called ice, right? And my solid water has particles in it, and you can see they're vibrating there. When I press the play button, the temperature starts to go up. And I notice it melts, okay? So I can pause it at any time. I can see the particles, I can see the temperature, and I can watch what's happening on the graph. In addition to that, I can change my starting state and my final state. So I can change this final state to be a gas, and you'll notice when I click that, it started all over again. So let's watch the whole thing play through once. So I've got a solid, my particles are moving. This melting is happening at this flat part of the graph. Particles are moving more and more. I just want to pause it there just for a second, okay? Notice I'm at 0 degrees Celsius. I've got a little bit of ice and actually a lot of water. I paused it there. So I'm both ice and water at this point where it's melting. So I'm going to hit play again. It sticks at 0 for a while, and the particles start to move more, and all of a sudden we enter the liquid phase. Now you'll notice when we enter the liquid phase that it's starting to heat up, but you may have seen that there are particles that are exiting that liquid. So we're only at 31 degrees Celsius. We are not near 100 degrees yet, and there are already particles that are starting to leave from what looks to be the liquid phase up into that gas phase. So let's watch what happens the closer we get to a gas. I notice that the particles are moving more quickly. All right, they start to kind of vibrate more and move more past each other. And maybe more and more are coming out of that gas or that liquid into the gas phase. So now we've entered that 100 degrees. Notice here, at 100 degrees, it switches down here to vaporization, it says. It doesn't say boiling, it uses the word vaporization. We can see lots of steam coming out and lots of particles are leaving my liquid phase. So if I keep watching, those particles keep moving more and more, and more particles keep leaving my glass. There's less and less liquid inside the cup. Particles are moving more and more. I'm at 100. And now I'm at vaporization. Now, interestingly, it looks like most of my particles are gone, but it was nice enough to leave a few behind for me that are bouncing around on the hot plate. And those few particles that are in the gas phase are getting hot. They're going over 100 degrees. So that's because I clicked my final state here to be a gas, okay? Or we can go back in the other direction, okay? And I like the way that they kind of change the background there. They kind of freeze it. So now we're going to work our way down the graph, back down from 50. We're cooling off. The particles are definitely slowing down. And then we hit 0 and that ice starts to form, okay? Freezing is when it's both liquid and solid. And then we're going to go down to the solid, all right? And once it's the solid, we can cool it more and more. Now let's take a look at the Schoology quiz, all right? It says, does the temperature of liquid water increase while it's boiling? Well, we know that from not only the simulation, but we've been looking at this graph, right? So we know that liquid water, while it's boiling, liquid water is not going to increase. Nope, it is not going to increase. Okay, next question says, which best describes the relationship between molecular motion and energy? As more energy is added, the molecules slow down. As more energy is added, the molecules speed up. The energy does not have an effect on molecular motion. Well, we saw in the simulation, as we added energy, and in this case, it's really similar to the graph we were looking at before. Before it was time, but now it says that it's heat in something we call kilojoules. And you don't have to understand exactly what that is, but heat is a form of energy. And so maybe that's why this one was tricky. As more energy is added, the molecules are going to speed up. All right, number 3, when you boil water, why does the level of the liquid decrease? Well, we saw this in the simulation, and I'll show you again for a second here. If we've got liquid and we're heading towards a gas, we notice as it starts to rise there are little particles that are leaving, okay? So the particles are leaving, but they're leaving as whole particles, whole water molecules. So it says when the water boils, it disappears. Well, no, it doesn't disappear. It doesn't go anywhere. As the water boils, it boils over too much. Bubbling the water ends up outside the cup. Yeah, we didn't really see that happening. When you heat water to boiling, it turns to hydrogen and oxygen gas. Let's check again. Do we see any changes in different hydrogen? And there's boiling. Nope. It's still just water molecules leaving, right? They look like water molecules. All right, as water boils, the water molecules leave the liquid phase and are released to the gas. I like that one. And it says, when the water is heated to the boiling temperature, the liquid compresses so the level decreases. No, not looking good. So I'm going to choose this one. All right, now this is an interesting graph. We've never looked at this guy before. This one says solid, liquid, gas, and instead of going in a straight line, like maybe our graph does here, it's linear. This one goes around in a circle. So it says solid, liquid, gas, and let's see what words they want us to put. All right, melting, freezing, condensation, evaporation. Interesting. Now, my simulation did say vaporization. Let's do the ones that I know. I know from the simulation that when a solid turns into a liquid, that's this arrow, we call that melting. When a liquid turns into a solid, we call that freezing. So now what we're left with is evaporation and condensation. So let's take a look here and see if we have a gas and we want to go to a liquid. Notice they've got a cover on the cup there, so our gas particles are filled in. Okay, they do write the word condensing. Condensing, they do right there. So let's go ahead and write and say from a gas to a liquid is called condensation, which leaves one more here, evaporation. So we're going to put this because it's what's left. But is evaporation the same as vaporization? Maybe it is. Maybe they are the same word. Maybe they're a little different. I don't know just yet. In our classroom environment, can pure liquid water exist at 100 degrees Celsius? Well, we were just looking at that one, actually. And you can see here, if I restart this, 110 degrees, nah, we're not going to get a liquid there. We've got gases. So no, pure liquid does not exist. We are all in the gas phase at that point. As a change of state takes place, for example, it gives you from ice to water. Heat does what and temperature does what. So we've got a solid moving to a liquid. All right. As we move here, there's the change of state right there. We call that melting. We call that melting. So heat is going in to the system. All right. Temperature is staying the same. So heat increases with the graph. Heat is increasing from ice to water. We are putting heat into the system, but temperature is staying the same. All right, that's because we're at that flat part of the graph. A change of state is a irreversible or reversible process. Well, we've been going back and forth. We can flip them back and forth from solid to liquid, liquid to gas. So it is definitely a reversible process. We can go in both directions. Multiple may be correct for this. What is the difference at the molecular level between a solid and a liquid? All right, so I happen to have them right here. Here's some liquid and here's solid. What is the difference? Is the molecule the same? Yep, they're both water. Same type of molecule, water molecule. How about the strength of forces between the molecules? I don't know about that yet just by looking at this, but I could make some predictions. How about the speed? We definitely know that the speed is going to be different. So the one I'm not really sure about is that strength of forces between the molecules. Is there any evidence here that would suggest? Well, if you're looking at the ice phase, you're going to notice that the molecules are staying put. In the liquid phase, they're moving around. So it does turn out that that strength of force between the molecule is going to be different. Which of the statements below is true? There can be a change in heat without the temperature changing. Heat remains constant throughout the change of state. Temperature changes throughout the state change, or heat and temperature are the same. Well, let's knock this one off right away. Heat and temperature are not the same. Look at, they're two different things on the graph. I've got temperature over here and heat down here. So we're going to be talking about one changing, one staying the same, okay? Heat is the x-axis at this point. So heat remains constant through a change of state. That is not true. If we look here closely, this is a change from a liquid to a gas. The heat increases by 20 kilojoules. It goes from 40 to 60. So heat does not remain constant through the change of state. However, temperature at this part in the graph does remain constant. So there can be a change in heat without the temperature changing. All right, that's the only one that works. Now, rank the states of matter from the slowest to the fastest. We have looked at this a couple times in the simulation. The slowest are going to be those solid particles, followed by the liquid, and then finally the gas is the fastest. When heat is removed from a solid, what happens? So I'm going to have to think about this one theoretically. Let's take a look at my graph here. I'm here at a solid. I'm going to move in this direction. I'm going to make it to there on the graph, okay? The particles move faster. The solid becomes a liquid. The particles move slower or nothing. So I'm not melting. I'm just going ahead and I'm moving those particles slower. It's important to remember where you are on this graph the entire time. Describe the movement of solid particles. All right, so if I have solid particles, look at them. They are moving. They are definitely moving. They're kind of jiggling there in place, okay? So they're moving. They're not moving fast. They're not flowing. They're kind of vibrational, right? If you watch them in here, they look like they're kind of vibrating there when they're in the solid. And the last question, as the speed of the particles decreases, intermolecular forces. So again, we're going to talk about those forces between the molecules. This is something we haven't gotten into very much. The only place that you can really see it is when you start looking at those particles, whether they're moving around. How are those intermolecular forces? Those forces that are between each particle. As the speed of the particles decrease, intermolecular forces become stronger, become weaker, don't change, cause the energy to change. Okay, well, we don't really know the answer to this. This is a straight up guess at this point, based on what we're looking at. But I would guess, since the particles are slowing down, those intermolecular forces are probably holding those molecules together more. Okay, so those intermolecular forces are actually becoming stronger. Okay, Now, I had a lot of questions about the intermolecular forces, and I'm sorry to have stressed you out about them. They're not super visible in the simulation, but I wanted to get you guys thinking about them, okay? Intermolecular forces are just that. They're the forces between molecules. All right, so that's it. Those are the answers. Let's hope I got them all right, and have a good day.